Welcome back for this afternoon session. So the first speaker is Dante Luber from Frankfurt, and he will talk about singular Matroid realization spaces.
Thank you. Can you hear me? You hear me? Yeah? Okay, thank you for the introduction. Thank you for having me here and giving me time to talk about this. So yeah, I'm going to tell you about some joint work I did with Dan Corey when we were both in Berlin. And we're going to talk about realization spaces of Matroids. So I'm going to be talking about software a lot. And the software system that we used for this project is called Oscar. And so that's an open source computer algebra research system that integrates capabilities of Singular, Polymake, Gap, and I think a few other software systems for math. And we're going to use Oscar to study moduli spaces that you extract from Matroids that consist of linear objects. And we're going to use the algebraic geometry associated with these spaces and matroidal subdivisions of hypersimplices to say some things about initial degenerations of Grassmannians. Before I move on, I just want to quickly say, we're going to be dealing with realizable matroids, right? And one way to get a realizable rank D matroid on n elements is to take some matrix with entries from a field, a D by n matrix of full row rank, and then just say that the bases of your matroid, I'm going to use Q, say QA, the bases are the labels of the D by D submatrices that have non-zero determinant. Yeah? And you can extract a matroid from a matrix, and then that process gives you a decomposition of the dn Grassmannian into substrata or subvarieties indexed by matroids, right? Because you can represent an element of the dn Grassmannian with a D by n matrix. Yeah? Okay, so that's hopefully all the board work I'm going to have to do. And so yeah, so I just explained how if you have a dn matroid, you have a subvariety in the dn Grassmannian associated with that matroid. So we're going to call those matroid stratum. And then in other talks, we've been hearing things about matroids that we get from hyperplane arrangements. Yeah? And I mean, I'm going to be kind of, I guess, loose with talking about the moduli space of hyperplane arrangements which parameterize a matroid, or the moduli space or the substrata in the Grassmannian corresponding to that matroid, because these things are very closely related by this thing called the Gelfand-McPherson correspondence. Yeah, so if you take your stratum in the Grassmannian indexed by your matroid, quotient out a torus factor, you get your realization space. You get the moduli space of hyperplane arrangements corresponding to that matroid. And what I'm going to talk about is how we study the algebra geometric properties of the matroid stratum or the realization space. Either way. Okay, and so, we're going to emphasize the rank 3 case. Yeah, what's nice about the rank 3 case is that you can encode rank 3 matroids with these point line configurations. So we have this weird line arrangement here with 1, 2, 3, 4, 5, 6, 9 marked points on it. And those marked points correspond to the elements of our ground set. And then the collinearities amongst those marked points give you the non-bases of your matroid. Yeah, so that's like saying there's some projective space with these points floating around, and the collinearities are like dependencies between those points. So those are non-bases. Yeah? And then 3 element collections that form a triangle that don't all fall on the same line, those give you your bases. Yeah, so these are kind of, I think we've seen other pictures of hyperplane arrangements encoding matroids, but I think these are dual to those pictures. Okay, and so why are rank 3 matroids interesting algebra geometrically? Well, there's this result called Minev universality or Minev-Sternfels universality that tells us that every singularity type appears on the realization space of some rank 3 matroid. And how does that work? Well, you take a scheme or a variety that has some defining ideal, and then you find a way to express the generators of that ideal in like a bigger coordinate ring, or in a bigger polynomial ring, using just these, they call them generic operations. So like addition, or multiplication, addition, negation, things like this, yeah? And then you can construct a line arrangement that has a subconfiguration corresponding to each of the generic operations you use to construct your presentation of the ideal. You extract a matroid from that line arrangement. That gives you a realizable matroid. And it turns out that the realization space of that matroid has the same singularities as the variety you started with. Okay, so that tells us that these things can be very interesting geometrically. But the problem with Meniyev universality is that it forces you to construct a matroid on like a really big ground set. So you have all these different generic operations, right? And then you have a subconfiguration corresponding to each of those. And those are what those subconfigurations look like. Yeah, so and then you have these like connecting configurations to form the big line configuration. So that forces you to have lots and lots and lots of elements of your ground set, which means it's not really like useful, I guess, or it's not really easy to take a singularity and construct your line arrangement and get your matroid that has that singularity on it, or whose realization space has that singularity. So yeah, our goal then, let me just say one more thing about how you can compute the data for these realization spaces. Despite them being complicated in their geometries, they consist of pretty straightforward data. So we're going to assume that 1, 2, 3 is a basis of the matroid. And we're going to take a matrix that has the identity matrix in the first 3 columns and fill the rest up with variables. And well, what do we want? I mean, because of this right here, right? We want all the matrices such that the determinants indexed coming from columns indexed by bases, we don't want those to vanish. And if they're non-bases, we want them to vanish. So we're going to take the determinants indexed by non-bases, make an ideal out of those, and take the determinants indexed by bases and make a multiplicative semigroup out of that. And then we just then the coordinate ring of your realization space is just the quotient of the polynomial ring by that multiplicative, by that ideal localized with that semigroup. And that captures all the information you want. Okay, so that's like easy to compute in reasonable cases. And so to try to find reasonable examples that we can actually study of singular realization spaces, this is what we do. We just compute the data a whole bunch of times and check if the thing is singular. So, I mean, look, Oscar can compute realization spaces, or compute that data easily, right? And then it can also check for singularities using the Jacobian criteria. And since Oscar incorporates Polymake, and Polymake has this big database of matroids, we decided to just try to compute this data for as many matroids as possible going across that third row, or the row with, indexed by 3. And then check for singularities and look for something interesting. Okay, and so here's what we found. We saw that for n less than or equal to 11, all of the realization spaces of 3n matroids were smooth. And then when n was greater than or equal to 8, for 3n, we started finding reducible realization spaces. But they were still smooth. They were like just disconnected pieces. And then when n equaled 12, we started finding singularities. And then just for fun, we checked n less than or equal to 9 and found everything smooth there. And then we developed these techniques. Well, all right. There are these operations on matroids called principal extension and principal coextension. And it turns out that if you take a matroid with a singular realization space, take the principal extension or principal coextension, that gives you a matroid on either a bigger ground set or higher rank and bigger ground set. Compute the realization space of that. That actually has the same singularity types as the thing you started with. So then with those operations and like matroid duality and stuff like that, we were able to construct matroids on bigger ground sets on a higher rank. And so this last result just says that there's, for d greater than or equal to 3, there's just finitely many dn pairs such that all realization spaces are smooth, just by kind of jumping around using those operations. Okay. So that's really it for now besides this example. So we have a 312 matroid there corresponding to this line configuration. And it's generated, or sorry, it's the corresponding ideal is generated by that single generator that factors into 2 elements. And then you can even factor that thing again to show that the realization space corresponding to this matroid is like 2 lines with a curve, and we have nodal singularities where all those components intersect. Yeah, okay, so that's one of the examples, but we actually found 76 examples of matroids with singular realization spaces in rank 3 on 12 elements, and our search was not exhaustive. I should say that. So there's more. All right, so the second part of my talk is about initial degenerations of Grassmannians. Have we seen like initial forms and initial ideals, stuff like that? Did that come up? Okay, so let's take the dn Grassmannian, and let's say that if we put a circle right there, that's the cell indexed by the uniform matroid, the stratum indexed by the uniform matroid. And so the tropical Grassmannian then is going to be all of the term orders that you obtain from vectors in R to the n choose d that give you non-empty initial degenerations of that open cell. Okay. And we've also seen matroid subdivisions of hypersimplices, right? So the Dressian is the subfan of the secondary fan of the hypersimplex that induces matroid subdivisions into subdivisions of the hypersimplex into matroid polytopes. And it turns out that there's this containment of the tropical Grassmannian in the Dressian. So what that means then is that if we have a non-empty matroid subdivision, sorry, if we have a non-empty initial degeneration, that gives us a matroid subdivision of the hypersimplex. So we get this interplay between algebra and combinatorics. So if you have if you give me a point in the tropical Grassmannian, we have a matroid subdivision of the hypersimplex and initial degeneration of that open cell. Well, the cells of the matroid subdivision are matroids, and each of those matroids has a stratum in the Grassmannian. The face containment of the cells in our matroid subdivision, that induces morphisms between the corresponding strata in the Grassmannian. And then the dual graph of the subdivision, that gives us a diagram to compute an inverse limit over where the morphisms are coming from the face relations. And what Dan showed a while ago is that if you have a point in the tropical Grassmannian, there's a immersion of the initial degeneration induced by that point into the inverse limit that we get from the matroid subdivision. So in some cases, you can actually use the properties of this matroid subdivision to study your initial degeneration. All right, so here's like a little picture of what's going on. So we have the 2,4 hypersimplex. We've seen that so far, right? The octahedron. And we have it subdivided into 2 matroid polytopes that intersect on a common facet, which is also a matroid polytope. Those 3 matroids, corresponding to the big cells in their intersection, those have stratum in the 2,4 Grassmannian. And we have morphisms from the stratum corresponding to the big matroids into the stratum corresponding to the smaller one. Yeah? That forms an inverse system, and we can just see that the inverse limit we get is the fiber product over those induced by that system. Yeah? So that's what's going on in like a really small example. You know, for more complicated Grassmann, or for higher DNN, we get more complicated pictures, right? But this is the idea. And so here are the results. So all initial degenerations of the open cell in the 3/8 Grassmannian are smooth. We found that out by taking all of the Matroid subdivisions, or all the symmetry classes of Matroid subdivisions corresponding to cones in the 3/8 tropical Grassmannian, and sorting them into different classes. So there were 57,344. And we sorted those Matroid subdivisions into 6 classes, and then just proved that for each of the combinatorial types, the corresponding inverse limit is smooth, and that there's a isomorphism between, and there's an isomorphism from the inverse limit to that initial, from the initial degeneration to that inverse limit. But in doing that, we had to prove that all of the 3/8 Matroid strata are smooth, because those are the things that correspond to the cells of our subdivision. And then we used the singular things we found to construct singular initial degenerations of the Grassmannian using the same technique. You use the co-rank vector of your Matroid, and that has the Matroid with singular realization space. That has the polytope of that Matroid as a cell in the subdivision. Compute the inverse limit over that subdivision, and the structure morphism gives you a map from the inverse limit to that Matroid stratum that preserves the singularities, and then that inverse limit includes into that, and that preserves the singularity as well. So my main question that I took away from a lot of this stuff was, how does the combinatorics of a Matroid influence the geometric properties of its realization space? I'm not sure if there's any relationship at all. Maybe there is. And yeah, that's really it. For more information, everything I talked about came from these 2 papers. And yeah, I mean, I said it a million times, but the software we use is Oscar, and all of the code and stuff we wrote to do this project is available in Oscar, so you can use it yourself to study realization spaces of Matroids. The end.